Okay, so we need to talk about nuclear stability because radioactivity happens spontaneous if a nucleus is not stable. So what makes an isotope undergo radioactivity? Simply that it is an unstable isotope. So what is going to make it unstable? We have talked about one of these. That is anything greater than 83. But why is that true? The density of our nucleus is extremely high. What does that mean? That means you've got a lot of matter squeezed into a very, very tiny space. So look at that number for density. 2 times 10 to the 14th grams in a cubic centimeter. There's this unfathomable density. Let's think of gold. Gold is like 20 grams per cubic centimeter. Okay, those electrons are taking up a lot of, just spread out and gives us a lot of empty space. And so elements themselves are not near that dense, but their nucleus are. Okay, so we have got a lot of protons packed very tightly in a small, small space. Now, the neutrons are in there in order to overcome the fact that those protons are trying to repel. Okay, they are opposites attract, but same charges repel. So those neutrons are in there to allow some attractive force. Something's got to hold them together, and it's those neutrons that are in there to enable that to happen. So we've already stated that anything greater than 83 is just too many protons, and there's not going to ever be enough neutrons to stabilize that. But the other thing that's important is the proton or the neutron to proton ratio. Okay? For however many protons you have to have enough neutrons. So this neutron to proton ratio plays a role in stability. Now this is kind of a sub-point, but it is one of our learning outcomes to know this. Any particle in the nucleus is called a nucleon. So when you hear that term nucleon, we're talking about our protons, we're talking about our neutrons. They are nuclear particles called nucleons. Okay? That neutron to proton ratio for the small elements needs to be around 1. Okay? 1 is a stable isotope. So we did, when we were balancing nuclear reactions, we did calcium, and there was a 20 here, and there was a 40 here. Okay? The 20 is the number of protons. The 40 is the number of protons plus neutrons. So this guy had 20 neutrons. So that would give 20 neutrons and 20 protons, and that is 1. That would be a neutron to proton ratio of 1. But when they start getting bigger, they won't be stable with that. You need to have that neutron to proton ratio increase as it gets heavier and heavier, as you get more and more protons. And we're going to look at this belt of stability here. What you see in blue, okay, are your non-reactive isotopes. They are the stable isotopes. What you see in black is the 1-to-1 ratio of protons to neutrons. So you can see down in this region, 1-to-1 gives you stability. But when you get up here, let's look at this guy right here. We have 70 neutrons and we have 50 protons. So that is a stable nucleus. If it were 70 and 70, all right, that would be over here, but there's no stable or even unstable, because all of those things in green are your unstable nuclei. You don't even have an unstable one. There's nothing that even exists to be unstable in any way, shape, or form once you get up there to numbers like that. So let's find 83. When we get up to 83, there is nothing stable beyond that. Everything here is, they do exist, but they're unstable and they will undergo radioactivity. Now the type of radioactivity they undergo depends where it falls within that belt of stability. So if it's up here, it's got too many neutrons. If it's down here, it's got too many protons, and it will undergo different types of radioactivity depending upon that ratio. All right, so that is why we undergo radioactivity.